Hola, pessoal. Hi, my name is Leo Dirac, and I'm really excited to be joining all of you in Portugal and around the world. I was really hoping to get out to Lisbon sometime this year. I have some good friends living there, but given everything, I guess this is as close as I'm going to be. So, hey, it's great to see y'all. So today I'm going to be talking about configuration space and helping you to try and understand some of the geometry that's going on inside of it. And I think this is a really useful set of tools. So to start out with, I'm going to define what I mean by configuration space, and then show you some real examples of what it actually looks like inside of it. And then we'll talk about how to use machine learning and model configuration space with a process called Bayesian optimization, or BayesOpt. And then I'll give you some practical tips for hyperparameter optimization, or HPO, which is something I've been passionate about ever since I started training deep neural nets in 2013. I've always wanted to automate the process of tuning those darn hyperparameters, and I've spent years to do it and built commercial products to do this, and I'm going to share a bunch of what I learned about it. So to start out with, what do I mean by a configuration space? So what I mean is the choice of every possible thing that you can tweak about training a machine learning system represented as a vector space. So you probably think of this as hyperparameters, and you're absolutely right. Things like the learning rate in the optimizer, or the amount of dropout that you're using, or whatever regularizer you're using. These are tunable things that just don't have any correct answer. But also the expressiveness of your system, how many layers in your neural net, or the embedding dimension. And to be clear, everything I talk about here applies to classical machine learning just as well as deep nets. But I love deep nets. I think a lot of you do too. So that's what I'm going to use as my examples. Also, things you do in your data handling can also be expressed in your configuration space. If you're augmenting the data or downsampling it, anything like that, doing feature engineering, these things can show up as configurable parameters and should be considered part of configuration space. But even more generally, beyond that, any algorithmic choice can be considered this way. Which neural network architecture you use. If you just have a new idea and you expose it as a Boolean flag, and you say, if yes, run this chunk of code. If no, run this chunk of code. These are choices that show up in your configuration space. Some real world examples. Here's YOLO with a couple dozen hyperparameters that it exposes. Or consider XGBoost, which is probably the biggest workhorse in industrial machine learning and probably runs more real predictions than anything else today. Last time I checked, it has 42 hyperparameters you have to pick to run the thing, which is kind of nuts. So configuration space encompasses all of these different choices and represents them as a vector space with a dimension for every hyperparameter, every choice you have, unless you have categoricals. And then the standard thing to do is to use one-hot encoding and define a new dimension for every choice. A little inefficient, but it works. Okay, so now we've talked about what I mean. What does this thing actually look like? So if you draw some pictures, like what can you see inside of these configuration spaces? So I ran some experiments using the classic MNIST dataset, represented flat, running through a fully connected MLP network. And I built a really screaming fast implementation of this thing that can run 15 epochs per second on a single GPU that let me do tens of thousands, hundreds of thousands of evaluations to draw these charts for you. So you can really see definitively what this space looks like. So to start out with, I just ran a line search on SGD, a single dimensional configuration space, to get a sense of what one of the most important and commonly tuned hyperparameters is, the learning rate. And you can see there are these blue spaces up at the top, which are 90% error, and that means it's random guessing. It hasn't converged at all. And then the very best results down at the bottom are getting maybe 2% error, and those are bright pink, and that's what we want. So we see there's this big wide range where as you increase the learning rate, the results get better and better and better until you hit this wall, and then it suddenly falls apart. So if we switch to adding Nesterov momentum on our SGD, I call this a different optimizer, then we see a similar pattern, a very similar pattern in fact. The bottom is maybe a little bit deeper and slightly lower, but it's the same basic shape. And if we switch to the popular Atom optimizer, again, it's the same basic shape, but it's got some important structural differences. Now it doesn't have this very sudden cliff at the end. It's got kind of more of a smooth bowl, and the ideal values are much bigger in the middle. And to zoom in on all three of these and just look at what might be considered reasonable results, where you're getting less than 5% error, I apologize for how these charts are laid out, but I'm trying to make them about the same on the vertical axis to emphasize the fact that Nesterov is actually getting you the best results in this case. When you look at slightly better than SGD, and if you look closely at Atom, and here I ran a bunch of repetitions varying the random seed for every learning rate value, and you can see that Atom, there's no value of the learning rate that reliably gets you a good answer. And none of them are as good as what Nesterov gives. And so this underlies an intuition that I've developed, and I think a lot of people have learned over the years, which is that, in summary, Atom is awesome because it's robust, it's super fast, it reliably gets you a pretty good model. But if what you want is the really best model that you can get for your data, you got to switch to SGD or one of its variants and wait. Not always true, but often the case. Okay, let's add another dimension to our configuration space and see what it looks like. So we're going to spend a lot of time varying the dimensionality of the hidden layer, the fully connected dimension here, which is what's on the vertical axis, ranging from 10 to 10,000 here. And we can see that there's this sort of knife-shaped thing where there's some reasonable results, but the very best results are in this narrow little pink sliver. And so one common pattern that I want to emphasize, it shows up all over the place in configuration spaces, is that there are these big, bad open areas, these dark blue seas where nothing good happens. And so if you're throwing darts at a board, there's a good chance that you're going to hit something that doesn't converge at all, like literally not at all, or gives you just really bad results. And that the best results are these narrow slivers in configuration spaces. Another common pattern is that many hyperparameters are highly, highly correlated. So here I'm looking at momentum and learning rate, or log 1 minus momentum. So 0.9, 0.99, 0.999 are all evenly spaced on this chart. Over many orders of magnitude of learning rate, the two are highly, highly correlated, which makes sense if you think about what the momentum is doing. It's speeding up each jump through parameter space that the optimizer takes if it's getting the same signal over and over again. So if you decrease one, increase the other, it has about the same effect. And you can see this pink band is diagonal over many orders of magnitude. And the same idea shows up, batch size is super important here as well, because batch size is highly, highly correlated with learning rate. We should really talk about learning rate per record, not learning rate per mini batch, because learning rate per record is much more stable. But that ship sailed decades ago. Anyway, if you look at the number of epochs versus the learning rate, you also see a big correlation. You need a certain amount of learning to be done, and if you don't have enough epochs, you can kind of make up for it with a higher learning rate to a point. So these two are pretty highly correlated, but you see this interesting kind of triangular shape. So these correlations are another common pattern that shows up in configuration spaces. And these can be, they're pretty easy to see in these two-dimensional plots, but they get problematic in higher dimensions, because let's say that the high-quality pink band is occupying 5% of the space when we're looking at 2 dimensions. When we add a 3-dimension, if everything's equally scaled, you're only going to have 1% of that space, which is giving you those high-quality results. And if you add a 4th dimension, it's going to go down to 1/3%. And as you increase dimensionality, the volume of the high-quality configurations goes down exponentially. And this is really troublesome for trying to find a high-quality configuration when you have dozens or 42 hyperparameters to choose from. And this is an example of a really common phenomenon in machine learning known as the curse of dimensionality, which basically says that high-dimensional spaces are just really, really big. And there's not much to do about it except to realize that this is the case and figure out how to deal with it. Another important common phenomenon in configuration spaces is what's called double descent. And up until now, all the things I've been talking about are probably pretty well understood to a lot of folks who've been at this for a while. And so if you're dozing off a little bit, Now is the time to wake up, okay? Hey, everybody, this double descent stuff is new and it's important. It's really, really cool. The first research on this was published just a couple years ago, and I'm going to show you this. This is really interesting. If you haven't seen this before, please pay attention. So to look at this, let's look at the correlation between a couple other hyperparameters that we think are related, such as the expressiveness, the hidden dimension size, and regularization. I'm using dropout here. So when we vary the hidden dimension size and the dropout over pretty big ranges, we again see that they're strongly correlated, but in this kind of arcing shape now instead of a simple diagonal. And interestingly, in this setup, the very best results come with these huge hidden layers of thousands of dimensions and this kind of obscenely high dropout value of like 0.9, where almost everything's getting thrown out during training and ignored. This kind of makes sense. Make it big and regularize the heck out of it, and that gives you a good model. But then there's something different going on at the bottom. You see that green hump shape? What is that? That is an example of double descent. And double descent is interesting because it reconciles two key intuitions from machine learning that are in conflict with each other. So you take any basic machine learning class, classic machine learning, and it talks about the bias variance trade-off, right? We know that as we make the model more expressive, the error on the training data set goes down. That's what being more expressive means. It can learn more data. It can capture more complex relationships. But if you look at the held out test set, at some point, the error gets worse. This is just overfitting, right? We all know about this. And yet, in deep learning land, there's this other intuition that bigger is better, causing NVIDIA to train an 8 billion parameter language model, right? Bigger is better. We see this over and over again in deep learning. So how can these two both be true, right? They're in direct conflict. Either it's bigger is better or overfitting happens if it gets too big. So double descent explains how these are actually both true in different parts of the configuration space. And what happens is that as you increase the capacity of a learning system, the error or risk, as it's described in this original paper, will start to go down, and as the model gets better, and then you'll start to overfit, and then at some point it'll start to go down again as you cross from the classical regime to the modern or interpolating regime. And this crossover happens at this place called the interpolation threshold, where the system has essentially memorized the training data set, or at least is capable of memorizing the training data set, where the training error goes to 0, and this often happens around the point where the number of parameters in your net is equal to the number of records in your training data set. And beyond that, they call it interpolating, because the system has memorized the entire thing, and so it's just finding different models for interpolating between all of the training data that it's seeing. And so both of these intuitions are simultaneously true depending on how big your system is. And so we see this double descent curve over and over again. In language models, we see that as you increase the embedding dimension on a transformer, the error goes down, and then it goes up, and then it goes down again. Or if you look at CNNs, as you change the width parameter, you see the same thing. It goes down, it goes up, and then it goes down again. And there it is in our MNIST test. You see, as you go along horizontally at a fixed low dropout rate, the error goes down, and then it goes up, and then it goes down again. And you can see this in multiple ways. If we add a third dimension onto our configuration space and consider 1, 2, 3, and 4 layer neural networks, we see that the one-dimensional network is great. The two-dimensional network is not good. No choice of dropout and hidden size gets you a good result. It's overfitting everywhere. At 3 layers, it's starting to recover again, and at 4 layers, it's doing great again. And gosh, I wish I had known this 5 years ago, because the number of times I tried to solve problems with deep nets and it just wouldn't work, and the 2-layer network was just the best thing we could do, I was so confused. Now I know why. Anyway, we learn, we move on, right? That's part of the process. So double descent is super interesting. It shows up all over the place. We're really just starting to understand it, and you should look for it. It might explain some things you've seen too. And I'm sure there's lots of other patterns that show up over and over again in configuration space that we just haven't found yet. And boy, it'd be great to find some smart way to understand all of these. And so I asked this question: how do you find patterns in these high dimensional spaces, right? 5 and 10 dimensional spaces are really hard to look at and understand. Machine learners will call a 10 dimensional space as low dimensional space, but still they're really hard to work with. So there's this tool that we all use for finding patterns in high dimensional spaces, which is machine learning, right? So let's use machine learning to improve our machine learning, right? And this brings me to Bayesian optimization. So Bayesian optimization treats hyperparameter tuning as a supervised learning problem. So the way you do it is any supervised learning problem takes some input, runs it through a model to make some predictions. And here, the input is that vector in configuration space. And the regression problem you're trying to solve, you're trying to predict the quality of the final model that you train, the neural net that you train, which we're going to call the target model. That's what we're trying to predict. And we do this by training what's called a surrogate model, which tries to make these predictions. And so the basic algorithm of BaseOpt is to first define your configuration space that you're working in, pick the bounds, which things you're going to search over, and then pick k random points in this configuration all over the place just to warm things up, evaluate them, which is to say train a neural net on those k evaluations. Now you have a training data set, right? So now you can train your surrogate model. You have these k points with the vector inputs and the quality of the output. And now you search over the entire configuration space using the surrogate, which is much, much faster than training real neural nets, to just evaluate the surrogate and find where the best configuration is in configuration space according to the surrogate's predictions. Then you train a neural net on that surrogate. Train a neural net on that configuration, which the surrogate said was going to give you the best result. Now you have another data point. Go back, retrain your surrogate model, and repeat. Do this over and over again until you've got the best results. I like that, church. Sounds good, huh? So what do we want for a surrogate model? First off, it needs to be like, what kind of model are we going to use? We're going to use trees, we're going to use a neural net, linear model, something else. We need it to be data efficient, right? It needs to be able to work effectively on dozens or maybe hundreds of data points, because training these real neural nets is expensive. So we're not going to have millions of data points or billions like we do for classic deep learning, for common deep learning. We want the surrogate model to have quantifiable uncertainty. We want it to know the difference between when it's confident about something and when it really has no idea because it doesn't have good reason to in that part of the configuration space. And we want to deal with continuous and discrete variables. And we want it to be able to deal with conditional relationships, such as saying, only consider beta 1 and beta 2 hyperparameters if the optimizer that we've selected is Atom. So there are lots of things have been tried over the years, but nowadays most researchers have converged on using Gaussian processes for the surrogate model. And Gaussian processes do great at all of these except the conditional relationships. And it's like, oh well. So a GP, an awesome thing about it is it doesn't just make a point prediction. It doesn't just say the outcome is going to be, you're going to get 2.5% error. It gives you a mean and a standard deviation at every point in configuration space, which lets you trade off exploration and exploitation when you're picking the best configuration, which is critical here. It is extremely data efficient. If you're ever facing a really small data set in your problem, like maybe a medical data set where you have like 20 people or something in it, a GP is likely going to give you the best results. But the downside is that it scales cubically in the number of records that you have in your training set. So it can maybe do a few hundred records on a CPU. On a GPU that's 1,000 times faster, it can only do 10 times more records. The biggest one that I've ever heard of is from Andrew Gordon Wilson's group. They managed to train 1 million data points in a GP, right? But basically, they just can't handle big data. But that's okay, because here each record is a training run, which maybe took hours or days of GPU time. So that's fine. So some practical tips for hyperparameter optimization. BaseOpt is great. It is super sophisticated. You don't want to build one of these things yourself. Go find a tool. The big cloud providers have these things. I spent years of my life building the SageMaker AutoML tools. They're pretty good. There's other commercial offerings out there. And the open source offering from Facebook, Axe, is awesome. It's really, really good. I love it. But don't build your own. Try one of these. But there are plenty of problems and limitations with Bayes-Opt. So don't build your own Bayes-Opt tool. Use one of these. There's awesome ones out there. But Bayes-Opt has plenty of real problems too, plenty of limitations. One of them is that it's a black box evaluator. Like, the theory is all built around this idea that the outcome is a scalar, and all we're doing, all we care about, all we know is how to optimize that scalar value. So this is clearly not true. As we all know, as we're training a neural network, we can see all this data coming out in tensor boards, these learning curves that show the validation loss and the training loss as it proceeds. And I bet a lot of folks here have pretty darn good intuition about how to optimize your configuration if you see one of these 4 very different curves coming out of your training system. But all that Bayes-Opt sees is that one red dot at the end. All it knows is the final validation score. It doesn't see anything about the shape of the curves or anything at all about the training loss as it goes along. And so you're clearly leaving a bunch of information on the table using standard Bayes-Opt. In addition to the black box problem, it has this horrible cold start problem, which is to say, every time you run Bayes-Opt, it starts out not knowing anything about the configuration space. It has to learn everything about dropout and learning rate and everything that you've configured. There's no way to bring forward the old information you have, no standard way to do it. And also, Bayes-Opt is not aware of how expensive a configuration is. Changing things like the depth of the network or the width of it or the number of epochs has a huge impact on how long it actually takes to run an evaluation. And Bayes-Opt almost never thinks about this. So Bayes-Opt has plenty of problems, and in a lot of cases, it's not the best answer for what you're trying to do. In no small part because integrating with these systems is complicated, and so people very often build their own. And if you're going to build your own, you got to understand that random search will always do better than grid search if you're trying to get the best answer. And the intuition for this, it comes from this classic paper from Bergstrom and Bengio in 2012, which illustrates what happens when one hyperparameter is more important than another, which always happens. There's almost always some that just don't matter. If you're doing grid search, you're going to keep sampling the important hyperparameter that matters, the horizontal one, over and over again at that exact same value with different hyperparameters that don't matter. Whereas if you're doing things randomly, you always get different values for the one that matters, and so you map it out much, much better. And random is super trivial to implement. It scales super well. You don't need any communication between the processes. It's wonderful. Grid's good if you're trying to draw graphs and understand things, but if you want good results, use random. Another super important technique to be aware of and think about is Hyperband. So Hyperband, the great thing about Hyperband is it brings this kind of cost awareness. So the way Hyperband works is it starts out by picking a bunch of random configurations all over your space. Say you pick 1,024 random configurations and you run all of them, but just for a few epochs. And then you look at them, and some of them, it's going to be clear from the very beginning that some of them are doing horribly, right? And we know this as we watch processes manually, and Hyperband considers this as well. And it says, hey, I'm going to divide these in half. 512 of them, worthless, throw them away. The other 512 that seem like they're maybe all right, run those for another 5 epochs. And then after those 5 epochs, divide them up and take the best 256. Then keep the best 128, keep training those, and keep doing this over and over again until you get the one best configuration. And you've gotten there spending way, way less compute than you would have to evaluate all 1,024 completely. So Bayes-Opt will beat Hyperband will beat Bayes-Opt basically every time for small budgets. It very quickly can get to a really high quality result. For less than the cost of a single full evaluation with Bayes-Opt, Hyperband gets you something pretty darn good because it does these really small evaluations. But if your budget is big enough, Bayes-Opt is going to win, because Bayes-Opt has the surrogate model and it can fine tune and find a really good configuration, whereas Hyperband is never going to do better than one of those random guesses that it started with. So another technique that I love that we worked on at Amazon is what I call a pyramid technique. And it relies on the same intuition as Hyperband to use cheap evaluations to inform the configuration space. So if the problem is to understand this curve, this model, right, this configuration space, and find that bright pink area, with pyramids, we frame this as a transfer learning problem from a much cheaper related problem, which is running the same system on a downsampled data. So here is the MNIST run on only a quarter of the training data. And you see that the configuration space shape is almost identical. The best results are much worse, right? It only gets to like 6% error instead of 2% error, but the basic shape is basically the same. And this works as you go down to a 16th of the data or a 256th of the data. It's doing horribly. The best results are really bad, but you still see the basic same shape of the configuration space. And these are, can be a 256th cheaper to run. Here's even going down to an extreme. With just 48 records left in the training data set, throwing out almost everything, we can still see the basic shape of the configuration space. So the way that the pyramid technique works is to start out on a really cheap downsampled version of the problem and evaluate it all over the place. Do a bunch of evaluations and then use that as the basis to inform the next set of runs, which are using more of the data. And what we do is we treat the downsampling as what's called a context variable in the literature. So the downsampling ratio is another axis in your configuration space. It's like a hyperparameter, but it's one that we manually control instead of trying to tune. Because we know the thing to do is to do a bunch cheap, then learn more at a more expensive run, learn more at an even more expensive run. And then by the time you get to your full data set, maybe you only need to do a single run to get a great answer. So pyramid techniques have limitations, of course. We found that we got a 10x speed up on CFAR the first time we tried this compared to standard Bayes opt. And it's interesting to note there really is effectively no bottom for these cheap evaluations, right? You can do a very small number of records for a very short amount of training and learn something interesting and meaningful. But what happens is you run into the limits of systems engineering, right? The startup time becomes everything. And so that's why systems like this one I built, where it can restart a new training run in milliseconds instead of, say, minutes, in a system like SageMaker that turns on a new EC2 instance every time you launch a job, is critical. So there's a real trade-off. If you're going to do this, you probably have to end up investing a bunch in systems engineering to make it work efficiently. Also, the scalability of the surrogate model becomes critical, right? Because it's very easy when you're doing it this way to record many thousands of evaluations in order to inform your surrogate model and train it. And that's awesome in a sense, but if you're using a GP, then you better make sure that the GP scalability is going to fit with the amount of data that you're collecting. And the last thing I'll say about this is that you really need to consider the noise in the system. These systems have a high variance and it's real. You can't just set the random seed and have the noise go away. You'll get the same thing every time, probably, not always, if you set the random seed, but that doesn't mean that it's a robust configuration that doesn't have any variance. To do any of these things properly, you need to consider the fact that the results of any of these training systems are intrinsically stochastic, and that variance is important. And what you want to find if you're searching for a great configuration is one that gets you a good result reliably every time. And with that, I'm done. Thanks for your time. Thanks for listening. The code for generating these charts in that super optimized MNIST system is either already up on GitHub at this link by the time we're talking about this, or will be pretty soon. And so, again, thanks a lot.
Hey, everyone. We're back from Leo's talk. I'd like to throw a big thank you to Leo for this presentation. We were talking with Leo back in the green room, and he shared the fun fact with us. He's very into, I don't know if this is because of COVID, Leo, so correct me if I'm wrong here, but
that started before that.
Okay. So this was something before. He's very into Rubik cube solving nowadays, and he's actually responsible for creating, and I kid you not, a 12-meter Rubik's cube. that was displayed in Burning Man. Leo, I don't know if this is like a life a goal achievement, or go ahead.
I was a helper on that project. I wrote some of the code and did some of the electronics, but I was not the lead on it by a lot. A lot of it ended up in my garage too, but
Okay,
it was
okay.
a fun project. But I shouldn't take too much credit.
Okay, so Burning Man plus humility. Okay, there you go. Okay, so if you guys are already probably aware, Leo will join us now for the Q&A. As always, we'll be reading directly from the questions you have been posting online based on the number of upvotes. And there you go, Rubik Cube solved. So first question, let me just jump right into it. First question, Leo, hyperparameter optimization tends to be a difficult thing to learn for juniors. What would be the most important thing for a junior DS to grasp when they start to attempt hyperparameter optimization?
I would say that you should think of all of these techniques and tools as things that you can use. They're like tools in your toolkit, but not to rely on them too much. And that gaining intuition about hyperparameters is going to work better for you than trying to take a fully automated approach. At least in 2020 or 2021, like in 10 years, who knows, maybe these tools will get automatic and awesome. But for now, use line searches, vary one hyperparameter at a time and understand what that hyperparameter does, and then try another hyperparameter and do a line search on it and understand that next one. And I think that's the best way to start going about this, because another key thing is that many hyperparameters just don't matter. And so including them in a big search is just going to increase your dimensionality and make everything go badly.
Yeah, yeah, that's interesting. I hope this helps for whoever the person was that asked this. On the topic of, in the beginning of the talk, you were talking about bringing other metrics from outside of the usual hyperparameters as a hyperparameter. So another question that we have is, should energy consumption be a hyperparameter or a parameter in hyperparameter search? Let me rephrase that.
Yeah, absolutely. It's so an equivalent question there is, should I tune the number of epochs that I train for? Right? Should I vary how expensive my my training jobs are? Because you can try to predict ahead of time how much energy it's going to take, or you can just measure it. But the truth is that different training setups will cost hugely different amounts of energy and time and money, and they're all pretty closely correlated. And I think you should absolutely consider that as one of the things that you are optimizing for, because generally most people probably want to optimize not just for the best possible model, but the best configuration given a certain computational budget, which is either both the total amount of training time and compute plus the amount of energy, or compute per record, per inference, because you have to make your predictions in production in under 100 milliseconds or a second or whatever it is. So yes, it's a critical parameter to consider. Things like Hyperband do this automatically for you fairly well, especially if you have Hyperband vary the runtime instead of the number of epochs. Say, run for 10 minutes instead of one epoch. And then if different epochs take different amounts of time, it'll automatically adjust for this. So yeah, it's an important thing. You can't easily directly treat it as an input hyperparameter. It's more something that you observe, but yes, it's very important.
Yeah. And you mentioned it's also correlated with time somehow. So I guess if you're looking for non-tech metrics that you should look at, maybe those two would be paramount.
Yep.
A more specific question now, and I'll just read it ipsis verbis. When you are increasing the number of parameters, there is a point where you stop training a single model, but we are actually training an ensemble of specialized models. The bigger model could actually be working in two steps. One, classify input. Two, choose optimal submodel to treat that point. Would that explain the double descent phenomena? tell me if you want me to read this again, Leo.
No, I was been staring at that question for a while. It's been on
There
the
you
board,
go.
and it's a good one.
There you go.
Yeah, it's many techniques in deep learning can be considered as implicitly ensemble techniques. So, for example, Hinton showed early on that dropout can be viewed as an exponentially large ensemble of neural nets at every layer. So I think most, or at least a very large number of deep learning systems are effectively acting as ensembles. And sometimes this idea is explicit, such as in the sparse mixture of experts paper, where you explicitly train lots of neural networks and then have an attention layer that picks between the ones that are most relevant for any given problem. Um, uh, does this explain double descent? I'm not sure. I'll be perfectly honest. I think that the fact that neural networks are ensembles is an intrinsic part of neural networks, and there's some great work that's come out just in the last few months talking about linear identifiability and ensembles. And I was just reading one of those papers last night. I haven't fully wrapped my head around them. I think some people might have a better answer for you than whether this is tightly coupled with double descent, but I don't know. I think it's super interesting stuff.
Leo, by the way, about that new work that you mentioned, if you want to share it on the event platform, if you have a link or the name of the
Sure.
authors, anything, feel free. Okay, I think that would be interesting for all of us.
There's
Cool.
three papers I'm really into right now. I'll post all three of them.
Share them, and we'll play along. I'm pretty sure.
Yep.
There's a question in first place that you kind of touched on my first question, but I want to readdress just to make sure that if you have anything to add, which is, can you tell a good strategy to look for the best parameters automatically for a classifier?
Okay, so I'm going to take a guess as to what the author of this question was wanting to hear, which is which parameters do you tune and which ones do you not bother tuning? Because that's a really important and difficult question. I hate to say intuition because that just means like work longer and gain experience, but the way to leverage other people's intuition is to look in the literature or blogs or what have you and see which hyperparameters other people are talking about changing, because those are the ones that other people are seeing value in messing with. And if you don't hear anybody talking about it, then it's probably not worth changing for you. I think that's the simplest way to answer that problem. There are analytical approaches. There is research published in exactly this problem. My team at Amazon did some work in this space, and it's super interesting. To dive into that briefly, there's this data set called OpenML where people publish configuration data. They just share publicly configurations and the results that they got training on standard public data sets. And there are millions and millions of entries in there. And so you can go mine these for analytically look at which hyperparameters people in this community are finding are more or less useful or important for what they're doing. So yeah, I'll dig up that paper as well and post it.
Okay.
But the easiest thing is just listen to what other people are doing and try varying those.
Okay, cool. Next question that we have, Leo. Is there any open source implementation of hyperparameter optimization with the pyramid technique?
Not that I know of. It's problematic for a few reasons. So if you're interested in this, Hyperband is the closest you're going to get. Mm-hmm. Hyperband does this approximately, and Hyperband is implemented in a bunch of places. So look for that. But the thing that's limiting about this is, like I say, the systems engineering part of it becomes critical as you push this limit to its full capabilities. And the open source platforms generally try to decouple the meta optimizer, the HPO code, from the runtime platform. They don't want, unless you're a big platform like, Amazon or Google, you don't want the tuner to be tightly coupled to the way you run your jobs. People have many different ways of running jobs. And the way you run your job becomes critical, especially the startup time and the restart time are critical for using pyramid techniques. And so it's a difficult thing to publish as open source separately from something that does the training itself. And most people, when they get down to it, like to write their own training code. I suppose if you're using Keras or PyTorch Lightning or something,
Yes.
which are pretty high level, it would be possible to build something like this that works for a lot of folks. But that's the challenge, I think, with sharing this kind of code broadly.